Chemoselectivity is a useful principle of retrosynthetic analysis which tell us the disconnection of a more reactive group faster than the less reactive group. Consider an example. Where we have two choices of disconnection. Let me make a disconnection next to oxygen atom right over here and call it disconnection A. I will get two syntones. A phenoxide, which is a good syntone for a phenolic moiety, and a positive charge right over here and phenol. Both these syntones are equivalent to their corresponding reagent of as we have positive charge on benzylic carbon atom, therefore it is more appropriate to put an electronegative atom for making a suitable reagent. Let me call it reagent A. This structure can further be disconnected right over here for getting a para-hydroxyphenol and 1,2-diabromoethane. This is 1,2-diabromoethane. I have also a second choice of disconnection as well right over here. Let me call it disconnection B. I get one syntone and another syntone can be like this. Both have equivalent reagent of 1,2-diabromoethane and a phenolic moiety. Which can be disconnected right over here for getting a para-hydroxyphenol and species like this. Let me call it reagent B. Now the question is which synthetic route is appropriate, whether the synthetic route A, which I have shown with the red sketching, or the synthetic route B, which I have shown with a blue sketching. Here we need to focus as one of the reagent which is from phenolic moiety that is same in both cases. Here we have this fragment as same, but the reagent A and B are different, whether we consider a reagent A or a reagent B, so both are different. Generally the phenol moiety is exposed to react with base for giving a phenoxide, and this phenoxide then react with either reagent A or B. Now the question is which reagent is more reactive, whether it's reagent A or B. Here reagent B is more reactive because this carbon atom where an SN2 reaction is performed by a phenoxide ion then the reagent A, because the benzylic carbon is less reactive as compared to this benzylic carbon is less reactive for an SN2 reaction as compared to the carbon atom of 1,2-diabromoethane. So therefore we can say that the synthetic route B is appropriate and it is correct, unlike the synthetic route A, which is not feasible for making this retrosynthetic analysis. Consider the synthesis. We will first react, let me call or number the reagent for clarity or simplicity. This is 1, this is 2. I will react 1 plus 2 in the presence of a basic medium, so that I get a phenoxide ion, and this phenoxide ion will make an SN2 reaction on reagent number 2, and we will get the reagent number 3. Let me call it 3. I will get 3, and this 3 will then expose to a basic condition, so to get the phenoxide ion again, and then the phenoxide ion will be reacted with reagent B to get the target material. Here this species is target material from where I have started. So by this way we can avoid the problem of a chemoselectivity. In synthesis, I react the less reactive group first and the more reactive group and the end of the reaction, because in synthesis we usually avoid to react the more reactive group because it can interfere with other moieties in a molecule. So in order to avoid it, we usually prefer to react the more reactive group in the later stages of synthesis. Consider another example with respect to synthesis of amine. For example, we have an amine like this, and we want to make its retrosynthetic analysis by making a disconnection right over here, and we get two fragments of primary amine and alkyl halide. So here the question of chemoselectivity can make the reaction worse, because whenever a primary amine are reacted with alkyl halide, then it cannot stop at second stage as in the target material, but it goes to multiple alkylation until we get a quaternary ammonium salt. Which can be, the target material will be ultimately transformed let me clear it like this. So we will get this quaternary ammonium salt instead of a target material. In order to avoid this problem, of chemoselectivity, we usually go via reductive amination or an amine formation, or we can choose the route of oxime formation. Consider the reductive amination route. Let's consider the target material. Let me clarify it a bit. I go for functional group interconversion so that I could make the disconnection AV. No, here I can make the CN bond of amide for disconnection, CN amide, and I get to the desiring reagent. So this is a feasible way. Consider the synthesis. The acid chloride will be reacted with the primary amine for generating an amide, and this amide will be then exposed to reductive amination or reduction in the presence of hydrogen and a catalyst for getting to the target material. As far as amine formation is concerned, let me follow the route B by making again functional group interconversion. Nitrogen, double bond here, this is an amine functionality. Let me know break. C double bond N, which is amine. Now I will get the reagent as primary amine and an aldehyde. So by this way we can avoid the problem of chemoselectivity. As far as oxime is concerned, we will consider an example of phenfluramine. Here we have an amide functionality like this. So this is our target material. This phenfluramine is a neuroactive drug. Let me go for functional group interconversion. By incorporating an amide functionality, let me break the amide bond right over here. I will get the primary amine right over here. And then via reductive amination I can go back to structure like this. Now consider the forward synthesis. Let me call it 1. I will react 1 with this reagent in order to get a species like this, which is a stable oxime. This reagent is then subjected to catalytic hydrogenation. Hydrogenation in the presence of a catalyst such as nickel, then I will get product number 2. This product number 2 is then treated with ethyl chloride, or especially species like this, in order to make a reaction on this amino group. This is an acid chloride, then I will get the species number 3 right over here, and this species then react with lithium aluminium hydride for reducing the carbonyl functionality, and I will get the target material. So by this way I can avoid the problem of chemoselectivity. And this is an example of fenfluramine. Let me revise important points. Chemoselectivity is important area of retrosynthetic analysis, which tell us that the disconnection should be made for a more reactive group first. Here we have given an example in which we have choose two different retrosynthetic routes. Only that retrosynthetic route was followed, where we disconnect a more reactive group first. As far as synthesis of amine is concerned, then the problem of chemoselectivity can be avoided by reductive amination, amine formation, or oxime formation. Here we have given an example of fenfluramine, which is a neuroactive drug. Here I have incorporated a different synthetic routes and reagents for getting the product, so that we could avoid the problem of chemoselectivity. Thank you for watching the video.